Hello. Today in this session I will wrap up what I have explained about transformations using matrices. In the past few sessions I have talked about how we can use a matrix to tell us the image positions of points on the xy plane for different types of transformations like reflection, rotation, shear, and so on. Now in those sessions I have just made up some examples of matrices for the various types of transformations, and I've not actually explained how those matrices come about. Now with some practice we should be able to remember most of them, hopefully, but it is good if there is a way that we can understand how those matrices come about, and better still if we can derive them on the spot, meaning that if I forget, is there a way that I can figure it out with a few simple steps? That would be nice. So that's what I'm going to talk about in this session. I'm going to try to explain how we can understand these matrices and how we can derive them when we need to. I'll start from the beginning again. Reflection in the x-axis. So that means that if I have a point up there, the image is down here. That's A, that's A prime. That's the image when A is reflected in the x-axis. So what is the matrix for this? How do we get it? The way to do this can be fairly standard actually. Now, the first thing to remember is that we need to think about the transformations on 2 points. Alright, for each type of transformation that we want the matrix, we need to think about 2 points. Now, which 2 points? That one and that one. So it's the points 1 and 1 on the x and the y axis. So that's quite easy to remember, just those 2 points. Right, and the coordinates of these 2 points, let's see, for that one is just write it down, it's 1, 0. That one is 0, 1. Now suppose now that I want to know the matrix for reflection in the x-axis. Okay, so I don't know what that matrix is in the beginning. So let that be a matrix with numbers A, B, C, D. So I don't know what the matrix is. I'm going to represent them with letters. Okay, so we are doing some algebra here. So let that be the matrix. And then I'm going to look at what happens when I apply this matrix to each of these points. So let me start with that one, the 1 on the x. That's 1, 0. Right, I don't know what these numbers are, what A, B, C, D are, but I do know where the image point for that should be if there is a reflection in the x-axis. Alright, because that point is on the x-axis. If I reflect about the x-axis, it's just the same point. The image point is just the same point. So my answer should be 1, 0. Okay. Now this is very useful because let's try multiplying out the left side. Now I'll do AB, first row and this column. So A times 1 is A, B times 0 is 0. Right? So the answer is A plus B, which is A plus 0, which is A. Now second row and column, C times 1, that's C, plus D times 0, which is 0. So C plus 0, C. So the answer for the left hand side is AC. And this must be equal to the 1, 0, must be equal to the image position. Now straight away you see that we have already found AC. A is 1 and C is 0. We have half the matrix, right? There are only 4 unknowns in the matrix and we have 2 of them. Not only that, now you see that what we've got here is AC, which happens to be the first column of the matrix. Now we have a very useful result here. What this seems to be telling us, right, is that the image vector or position or the coordinates, right, the image coordinates of the point 1 on the x-axis is actually the first column of the matrix. Now let's check out the next one. The point 1 on the y-axis. Okay, I've got the same matrix. I'll just write down the A, B, C, D multiplied by the 1 on the y-axis, 0, 1, should give me the image of that point. Now since this is a reflection in the x-axis, the reflection of that point of the 1 would become -1 on the y-axis. So the image point is at -1, 0. Okay, let's try multiplying the left side again. Once again, first row, first column, A times 0 is 0, B times 1 is B. So my answer is 0 plus B, which is B. Second row, C times 0 is 0, plus D times 1 is D. So I have 0 plus D, which is D. And this is -1, 0. And this time, notice that the I have BD down here, which just happens to be the second column of the matrix. So the second column of the matrix is the image position of the point 1 on the x-axis. So the image of the point 1 on the x-axis gave us one column, and the image of the 1 on the y-axis gives us the next column. And that is useful to remember. So in this example, alright, notice that I have used the points 1 on the x and y axis, okay, and on the left hand side I've done this calculation which gives me one column of the matrix at a time. And this does not depend on the type of transformation, okay? Whether it's a reflection or rotation or something else, it will affect the right side of the equation. It will affect the image. Alright, on the right side what you have is the image. The images. So the image positions will be different depending on the transformation. But on the left side, all I've done is I've taken an unknown matrix A, B, C, C, D, and I've either multiplied it by this, the position of this point here, or the position of that point here. So the right side of the matrix is the same regardless of the transformation, right? I would always have to multiply some matrix by either that point or that point. So that means that the understanding that we had, alright, we had here is the same no matter what transformation we look at. And the understanding here is that the first column of the matrix is always the image of the point 1 on the x-axis, that point. And the second column of the matrix is always given by the image of the point 1 on the y-axis. Before I go on to the next transformation, let me just write down the results for this. So, okay, I'll just write it here, reflection in the x-axis. So from what we have found, the first column should be the image of the 1 on the x-axis. So the 1, 0 there would be the first column, and the point 1 on the y-axis would be its image, which is minus 1, 0. And that should give us the second column. Right. I hope you have noticed that I've made a mistake here. It's right, that point should be 0, minus 1. Clean that away, it should be 0, minus 1. Right, minus 0 is the x, minus 1 is the y. Sorry about that. Okay, so the second column should be 0, minus 1. So then we have derived our matrix for reflection in the x-axis. So this means that the next time you need this matrix but you cannot remember, all you need to do is to think about these 2 points, the points 1 on the x and on the y-axis, okay, and you do a reflection or whatever transformation you have on the one on this point, and that gives you the first column, and then you do the transformation on the next point on the y-axis, and that gives you the next column. So let's try this out on all the other transformations. Okay, let's do y-axis. Right. Okay, let's get ready our matrix. So to find the first column, I should look at 1 on the x-axis. Reflection in the y-axis. That's the y-axis, that's my mirror. If I reflect that point, I come here, -1. And the coordinate of that point is -1, 0. That's my first column. Next, the point 1 on the y-axis. Right? Now since I'm reflecting in the y-axis, a point on the y-axis will just stay at the same point. The image is just the same point. So that point is 0, 1. 0, 1 is the coordinates, the position of that point. So there we have the matrix. Okay, moving on. Reflection in y equals to x. So that's this line. This 45-degree line. Once again, get ready our matrix. First column, we look at 1 on the x-axis, and we think about its image in this transformation. So, because that's a 45-degree line, this point, the point 1 on the x, will simply reflect to the point 1 on the y-axis. So that point is reflected to that point. So the first column would be the position of that point, which is 0, 1. That's my first column. Now let's go to the next point, the point 1 on the y-axis. The image of that point should give me the second column. So clearly, if that point is the image of this point, then this point must be the image of that point. Okay, so that must be my second column. And that is 1, 0. Okay, the coordinate of this point is 1, 0. So that's my matrix for reflection in y equals to x. Now let's do rotation about the origin by, let's say, I'll just put in some number, by 30 degrees. Okay, x and y. So following the same idea, I start with point 1 on the x-axis. The image of this point should give me the first column. Right, so when we say rotation by 30 degrees, okay, it always means in the anti-clockwise direction. If we say minus 30 degrees, it would be in the clockwise direction. So if I rotate this point about the origin by 30 degrees, it means that I think of this line joining the origin to the point. I imagine keeping the origin, the end at the origin fixed, and I imagine rotating this by 30 degrees. So this line would rotate up to there. Okay, so this line has a length of 1, so it goes up there, and this must be 30 degrees. Right. Now I need the coordinates of that point. So to find the x and y value, I drop a perpendicular to the x-axis. And from trigonometry, we know that the length of this is cosine 30 degrees. So that position must be cosine 30 degrees. And the y value must be this side of the triangle, which is sine 30 degrees. So those are the coordinates of the image of point 1, of this point 1 on the x-axis when it is rotated by 30 degrees about the origin. And this gives me my first column, cosine 30 degrees. Alright, and sine 30 degrees. My first column. Next, for the second column, we look at the 1 on the y-axis. Okay, we have to rotate that by 30 degrees as well. So if I rotate that by 30 degrees, it comes here. So let me clear this away to make it easier to see. I rotate by 30 degrees, it comes here. That's 30 degrees. So now, if I want to find the x and the y values of this image point, right, I'll drop a perpendicular to the y-axis. So this is a right-angled triangle, which looks just the same as this. Okay, and in fact, it is as if we take this triangle and rotate the whole triangle 90 degrees until it comes here. So therefore, since this is cosine 30, this is also cosine 30, and since this is sine 30 degrees, so this length must also be sine 30 degrees. Alright, that's the length from there to there. But because this is on the left side of the origin, we have a minus sign. So now we have the x and y values of this image point. They would be minus sine 30 degrees. Alright, that goes into the second column. For the x and for the y, we have cosine 30 degrees. There. So that's our rotation matrix. Well, these steps are a little more complicated than the reflection examples that we've looked at just now. And rotation is probably one of the more complicated, the rotation matrix is one of the more complicated matrix in geometrical transformation. So hopefully we have just finished with the most difficult example. So next we'll move on to let's move on to enlargement. So let's do enlargement with, say, a scale factor of 2. About the origin. So the origin is our center of enlargement. Alright, and we like to find our matrix. Once again, start there, 1 on the x-axis. Enlargement is about the origin. Well, I should just mention here that if the enlargement is not about the origin, then it is not possible to write down a single matrix to represent this enlargement. Okay, things gets a bit more complicated. And it's the same for rotation. So rotations and enlargement has to have the origin as the center if we want to use a matrix to do the transformation. Alright, so let's look at this point now. This point, we want to enlarge about the origin with a scale factor of 2. That means that to find the image position, we can imagine drawing a line from origin to this point. If you remember what I said in the last session, we draw a line from the center to the point, and then I multiply that distance by 2. So this distance here is 1. Multiplying 1 by 2 gives me 2. So that would take me to a point which is at a distance of 2 from the origin. So that's where I would be, and that's the image. So the image is at the position 2, 0, and that gives me the first column. Alright, for the next column we look at 1 on the y-axis. Once again we do enlargement about O. So from O to 1 the distance is 1. Scale factor 2 means I must take 1 times 2. Okay, and the image point would be at a distance 2 from the origin. So that's my image point, this point there. The position is 0, 2, and this gives the next column. So there we have our answer, the enlargement matrix. With some practice, as I have said, it should be possible to actually remember this matrix after some time without having to try and derive it on the spot. You might be able to recognize some pattern, like for example for an enlargement matrix, you would always have along this diagonal of the matrix, you have the same number, alright, and that number is a scale factor, and along and for the other elements there would just be 0. Let's look at shear transformation now. Let's look at this example where we have a shear in the x direction with a shear factor equal to 2. Alright, let's start with the 1 on x-axis. To find the shear matrix for this transformation, the first column is given by the image of this point, 1 on the x. Now if you remember, for a shear in the x direction, a point moves along the x direction, and the distance that it moves is equal to the distance from x, meaning it is equal to the y value of the point times the vector. Okay, which also means that if you have a point on the x-axis which is at 0 distance from the x-axis, that point doesn't move. If you do a shear in the x direction, any point on the x-axis stays. So the image of this point 1 is just the same point. 1, 0. Okay, let's look at the other point, 1 on the y. This point, when I do this shear in the x direction, would move along the x direction, and the distance is this length, alright, the height above the x-axis, times 2. So the distance that it moves is 1 times 2, which is 2. So it moves to there, right, from 0 to 2. So that's the image point. 2, 1. That's my matrix. So this is quite simple compared to the rotation. Let's do it for the y-axis now. I'll change the x to y. So now we want to look at shear in the y direction with the factor 2. So let's start again. For the first column, I want to look at the image of 1 on the x-axis. So this point, since it's a shear in the y direction, this point should move along the y direction like this. How far does it move? Right, the distance of this point from the y-axis is 1. And 1 times the shear factor 2, 1 times 2 is 2. So this point moves by a distance of 2. So its y value would be 2. Therefore, the first column is the position of this point, which is 1, 2. There we have our first column. For the second column, we look at the 1 on the y-axis. Right, and because this point is on the y-axis, it has 0 distance from the y-axis, it doesn't move. Okay, because 0 times 2 is 0. So this point has the same image as itself. 0, 1. And that's our shear matrix in the y direction with factor 2. So it's quite, can get it quite quickly. Right, one more example. We have stretch. Let's do a stretch in the y direction with factor 2. Right. And we start with that point, 1 on x. Now when we do a stretch in the y direction of any point, let me just draw any point. To find the image of this point, of any point, we must take its distance from the x-axis, that means distance along the y direction from the x-axis, and multiply it by 2. So this point would move up by until it is twice the distance from the x-axis. So that's how we do a stretch to a point in the y direction. And that means that if I look at this point, this 1 on the x-axis, this point has 0 distance from the x-axis. Okay, and since 0 times the factor 2 is still 0, this point doesn't move. So therefore the image of this point is itself is 1, 0. And that gives me my first column, 1, 0. Next we look at the 1 on the y-axis. Now the distance of this point from x-axis is 1. And 1 times the factor 2 is 2. So this point moves until it is at a distance of 2 from the x-axis. So therefore that is the image. And its position is 0, 2. And this gives the second column. So that's my stretch matrix for a stretch in the y direction with a factor 2. Okay, let's complete this with a stretch in the x direction. X direction. Once again, we start at 1 on the x-axis. So for a stretch in the x direction, I must look at the distance of the point from the y-axis. So the distance of this point from y-axis is 1. And I must multiply this distance by the factor. So 1 times 2 is 2. Therefore, the image point must be at a distance of 2 from y-axis. That's my image point. And its position gives the first column. For the second column, we look at the number 1 on y-axis. Now this point has 0 distance from the y-axis. And 0, since 0 times 2 is 0, so this point moves by 0 distance. Its image is just the same point, 0, 1. And that's the stretch matrix in the x direction with a factor of 2. So this completes our session and the past few sessions on transformation matrix. And we'll stop here for this session. See you next time.